Fischer projections are another way of visualizing molecules in 3 dimensions. And let's use the example of lactic acid. It's called lactic acid since it has a carboxylic acid functional group over here on the right. And this is the only chirality center in lactic acid. It's an sp3 hybridized carbon with 4 different substituents attached to it. So with only one chirality center, we would expect to have 2 stereoisomers for this molecule. And those stereoisomers would be enantiomers of each other. Over here, I've picked one of those enantiomers, and I've just drawn it in this fashion. Let's see which enantiomer we have over here. Well, this is my chirality center, the one attached to my OH. And if I were to assign absolute configuration to that chirality center, I look at the first atom connected to that chirality center. Well, that's oxygen versus a carbon over here in my carbonyl. So obviously oxygen is going to win. So we can assign oxygen a number 1 priority since it has the highest atomic number. And when I compare these 2 carbons to each other, I know the carbon on the right is double bonded to an oxygen, so that's going to give it higher priority than the carbon over here on the left since that's bonded to hydrogens. And then my other hydrogen attached to my chirality center is going away from me in space. So when I'm assigning absolute configuration, I look at the fact that it's going 1, 2, 3, it's going around this way, it's going around clockwise, therefore this is the R enantiomer of lactic acid. So that's all from a previous video. Now, if I want to draw a Fischer projection of R lactic acid, what I would do is I would put my eye right here, and I would stare down at my chirality center. So I would stare down at my chirality center, and I would draw exactly what I see. Well, if I'm staring down this way, I could draw a line right here to represent, my flat sheet of paper, and I can see that both my hydrogen and my OH are above my sheet of paper, whereas my carboxylic acid and my CH3 are below my sheet of paper. So this carbon is my chirality center carbon, and I have my OH coming out at me, and this is actually going to be on the right side. So if you take out your molecular model set, you will see this OH will be coming out at you, and it'll be on the right side of you. And this hydrogen will be coming out at you and be on the left side of you. So that hydrogen would go over here like that. This carboxylic acid functional group, right, this is the top of my head right here, then that would make this go at the top of what I'm looking at. And so that is going away from me in space. So we would use a dash to represent that, and so we could go ahead and draw our C double bond to an O and then an OH going away from me. And then if I look at this CH3 group over here, it's also going away from me. It's going down in space, so I can represent it going down in space like that. And this is the viewpoint of a Fischer projection. So if I'm going to convert this into a Fischer projection is just drawing across like that, and then at the top you have your C double bonded to an O and then an OH. Is just a way of abbreviating this carboxylic acid functional group. And then I have a hydrogen over here, and then I have an OH group over here, and then I have a CH3 here. So this is a Fischer projection. This is the Fischer projection for R lactic acid. So this is R lactic acid. And Fischer projections were invented by Emil Fischer, who won the Nobel Prize in chemistry for one of the things was for his research on carbohydrates, and he drew Fischer projections to help him draw carbohydrates, and so that's where you'll see Fischer projections used most often, even though some chemists don't really like them very much. So this is the Fischer projection for R lactic acid, and if I wanted to draw the Fischer projection for S lactic acid, I would just reflect this molecule in a mirror. So let's see if I can fit my mirror in over here, and I would have my OH reflected in my mirror, and then I'd go ahead and draw my Fischer projection, and then my methyl group would be over here, my hydrogen would be over here, and my carboxylic acid functional group would be right there. So this would be S lactic acid on the right and R lactic acid on the left. S lactic acid is the type of lactic acid that you find in the buildup of muscles after extreme exercise, and the type of lactic acid that some people have heard of from milk is actually a racemic mixture. So the bacteria in sour milk will break down the lactose into a 50% mixture of R and 50% mixture of S lactic acid. Let's take a look at a carbohydrate, since Fischer used Fischer projections for carbohydrates specifically. So here I have a carbohydrate, and if I were to number this carbohydrate, this carbonyl would get a number 1, and then this would get a number 2 over here, a number 3, and a number 4. This is a 4-carbon carbohydrate. How many stereoisomers does this carbohydrate have? Well, this carbon number 2 is a chirality center, and carbon number 3 is a chirality center. So 2 chirality centers. So I use the formula of 2 to the n, where n is the number of chirality centers. So I would expect 2 squared, or 4 possible stereoisomers for this molecule. So you could draw 4 different stereoisomers for this molecule. We'll draw them in a few minutes. For right now, I've gone ahead and drawn one of them as a sawhorse projection. So here I have a sawhorse projection of one of the possible stereoisomers. And what we're going to do is we're going to put our eye right up here, and we're going to stare straight down at this bond right here, and we're going to see if we can draw the Fischer projection for this molecule. So what do we see? Well, let's start with this carbon right up here. So we'll make that carbon this one, and you can see that the OH attached to that carbon is going to the right, and it's going up at us. So that OH is going to the right, and it's going up at us. And then if I look at this hydrogen over here, it's on the left and it's going up at us. So my hydrogen is on the left and it's going up at us. And this aldehyde functional group, this CHO, you can see is going down, right? So this aldehyde functional group is going away from us. So we can go ahead and represent that aldehyde as going away from us in space like that. Well, this chirality center carbon is connected to this chirality center carbon, so we'll go ahead and draw straight lines. It's looking straight down at it, and once again we will find that our OH group is on the right coming out at us, our hydrogen is on the left coming out at us. So let's go ahead and put those in. OH group is on the right coming out at us, hydrogen is on the left coming out at us, and then of course we have this CH2OH down here is going away from us in space. So we'll go ahead and draw that CH2OH going away from us in space like that. So that would be the Fischer projection translated. Let's go ahead and make it into an actual Fischer projection, right? Where we just go ahead and draw straight lines, and the intersection of those straight lines are where our chirality centers are, right? So this would be an H, this would be an OH. This would be an H, this would be an OH, this would be our CH2OH, and then at the top we have our aldehyde CHO. So this is one of the 4 possible stereoisomers. And Fischer projections just make it much easier when you're working with carbohydrates. So this is one of the 4. Let's go ahead and redraw the one we just drew, and let's get the other 3 to get our total of 4 on here. So I'm going to take the one that I just drew on the right, I'm going to redraw it, I'm going to draw it a little bit smaller so everything will fit in here. So this is one possible stereoisomer. I have my OHs on the right, I have my hydrogens, I have my CHO, I have my CH2OH. Okay, if I wanted to draw the enantiomer to this molecule, I would just have to reflect it in a mirror. Right? So I could just do this. I could reflect the molecule in a mirror, and I would have the enantiomer. So this would be the enantiomer to the stereoisomer that I just drew. If I wanted to draw the other 2, right, I can just go ahead and real quickly put in my Fischer projections right here, right? So I have 2 more to go. And I'm going to put the OH over here, and then the H over here, and then the OH over here, and the H over here. All right, so this is yet another possible stereoisomer. And I'll draw the mirror image over here on the right. So I have to have a hydrogen right here, and then my OH must be on this side. And then I have an OH, I must have an OH right here, and then a hydrogen on the other side, and then a CHO for my aldehyde, and a CH2OH. So here I have my 4 possible stereoisomers for this carbohydrate. And I'm going to go ahead and label them. I'm going to label this first one here stereoisomer A, stereoisomer B, stereoisomer C, and stereoisomer D. Well, C and D are mirror images of each other, so they are enantiomers of each other, right? So these are enantiomers. A and B are mirror images, so they are enantiomers to each other. And then we talked about in the diastereomer video, if I took one of the ones from A and B, right? So let me just go ahead and circle that. If I just took A, right? If I took one of the ones from A and B and one of the ones from C and D, I'll just take C, then A and C are diastereomers of each other. They are non-superimposable, non-mirror images of each other. So those are enantiomers and diastereomers to review what we covered in an earlier video. Let's do one more thing with Fischer projections. Let's assign absolute configurations to one of these stereoisomers. So let's just choose the first one, A. So we've been talking about A, and let's go ahead and redraw it really fast. And let's see how can we figure out the absolute configuration at my chirality centers from a Fischer projection. So it just makes it a little bit trickier than usual. So here I have my Fischer projection, and your aldehyde's going to get a 1, and then 2, 3, 4 in terms of numbering your carbon chain. I want to figure out the absolute configuration at carbon 2 here. So at carbon 2, what do I have? I know a Fischer projection tells me that if it's a horizontal line, everything's coming out at me. So my OH is coming out at me, and my hydrogen is coming out at me. Let's go back up here and stare down that carbon 2 chirality center, and let's see what we would actually see if we do that. So here is carbon 2 right here. I'm going to stare down right here this time. Right? So I have my OH coming out at me, my hydrogen coming out at me. That makes this bond and this bond actually go away from me in space. So the aldehyde is going to go away from me in space like that. So I'm going to go ahead and draw my aldehyde. Now I'm actually going to go ahead and show the carbon bond to one hydrogen. I know the carbon's double bonded to an oxygen, so I'm going to go ahead and do that. That was that trick we learned in an earlier video for assigning absolute configuration. And then the rest of the molecule is actually going down in space, right? So this would be a carbon here bonded to a hydrogen, and this carbon is bonded to an oxygen and a carbon. So what is the absolute configuration of this carbon here? Well, if I think about this is my chirality center. What are the atoms directly attached to that carbon? Well, I have a hydrogen, a carbon, an oxygen, and a carbon. Well, immediately I know that my oxygen is going to win. So I can go ahead and assign a number 1 to my oxygen right here. And then I think about what's next priority, right? Well, it would be carbon versus carbon. So the top, I have oxygen, oxygen, hydrogen. The bottom carbon, I have oxygen, carbon, hydrogen. So we saw in an earlier video, you go for first point of difference. So oxygen versus oxygen, no one wins. Then I go oxygen versus carbon, and oxygen wins. So this would get a number 2 up here. And then this would get a number 3 for my substituent, and my hydrogen would get a number 4. So I'm going around this way. I am going around this way if I ignore my hydrogen. So I'm going counterclockwise. So it looks like it's S. But remember, the hydrogen is actually coming out at me. So in the little trick I showed you in the earlier video, if the hydrogen is coming out at me, all you have to do is reverse it. So it looks like it's S, but since the hydrogen is coming out at me, I can go ahead and say with certainty that it is R at that chirality center. So at carbon 2, at this carbon, it is R. So you can do the same thing with the chirality center at the third position. So you could do the same thing with this one. And if you do that, you will find that it is also R. So you could go ahead and say for this carbohydrate, it is R at carbon 2, and it is R at carbon 3. So it is 2R, 3R, and it is a 2R, 3R stereoisomer. And you could do that for all 4 of the stereoisomers that we drew for this carbohydrate. And you could then compare enantiomers and diastereomers that way as well. So that's a quick summary of Fischer projections. Practice and use your molecular model set to help you with the visualization aspect.